Thank you. Good afternoon. I spoke at the first Bang Bang Con 10 years ago, so it means a lot to be here. I'm really grateful to all the organizers and to everyone. So I'm Omar. I'm going to talk about how to design your own microchip. And I wanted to start by talking a little bit about what a microchip actually is, to try to motivate like what exactly the thing we're going to try to design and get manufactured is. So the iconic image of a microchip is this little black rectangular thing, probably sitting on a circuit board, like this green circuit board. You probably think of like your CPU, your GPU, maybe your RAM. If you take about your phone or your laptop, you'll see a ton of these. But it turns out that as I was learning about this, a lot of other stuff is also made with a similar like semiconductor, photolithography, like the same kind of manufacturing process that I'm going to talk about is also used to make like the OLED screen on your phone is also just like a grid of little lights that's manufactured the same way. Solar panels, the radio in your phone is also made the same way. It's also a chip. A camera is also just like a grid of little light sensors that's printed on silicon the same way. The motion sensors, even a projector are like these little micromechanical things that are also fabricated the same way. So basically like all kinds of like, almost all like important technology that you might think of the last few decades is like designed this way, like drawn and then etched into silicon. So I wanted to learn how to make one. Like I wanted to learn how to make a microchip, or at least how to design one and get it made. I don't know, for the same reason that like, I want to know how to make an operating system or a programming language or whatever. I want to know how my computer works. I want to know how one gets made. So these are the chips that I designed and got made. I have one here, which I'll show later. They're in a little bag in my hand. This is one of them. So you can see there's the top side on the left, which is kind of shiny. So you can't, it's inside a package, right? So you can't actually see the circuit, even with a microscope, unless you like used acid to burn it off and then looked at it with a microscope, then you can see the circuits. So there are some people who do that. It's really cool. That's not what we're doing today. And then that actually does look like some of the diagrams I'm going to show. And then there's pins on the bottom, which you can use. They're kind of blurry here, but you can use the pins to connect whatever you want to connect the chip to, whether that's a screen or a radio or a mouse or whatever, right? Okay, so how does one get their microchip made? Let's say you have a design. You know, who do you talk to? Where's the factory? A few years ago, this free program started where Google and a bunch of other people, this chip fab Skywater in Minnesota were like, we want to support more people to learn about chip design, and we want there to be an open source chip design tool set. Kind of like there's open source C compilers or open source, you know, all kinds of other stuff. We want to have the same thing for chip design. So they started this program where if you put your chip design on GitHub, you can get it manufactured for free, which is pretty impressive because traditionally, if you wanted to have a chip design, if you wanted to have a chip made, you would kind of either have to be like working at a company that designs chips, or you'd be like an electrical engineering grad student, because it's really expensive to like make the mask and then like fabricate it in silicon. You know, this is probably like $10,000 of value of like this free program of like, oh, I'm gonna send in my chip for free and get it made. And this process that Skywater is, this process that Skywater is using to make chips is a 180 nanometer process, roughly. So for comparison, the top of the line chip in your iPhone 17 or your M3 Mac or whatever is like a 3 nanometer process. So, you know, it's a little bit outdated. It's like a GameCube chip or something. It's like 60 times, the logic gates are like 60 times bigger. You can kind of think of it as being than in the chip I made than in your iPhone 17. But still, you know, it's like, it's a real thing. So 180 nanometer process that we're talking about. This guy, Matt Venn in Spain, set up a course a couple years after this program started, which is what I took. I'm not affiliated with Matt, but I would definitely recommend checking it out if you want to learn about this stuff. He kind of assembled the curriculum and like put all the weird Python and Tickle tools in a virtual machine so you can just like run the command to synthesize your chip design. Yeah, like a lot of the stuff like that. And it's, you know, it's super approachable. Like it's not something you need to have like a ton of hardware background to learn how to do. Okay, so we want to make a chip. We know who to call to get the chip made. What do we actually want the chip to do? Like what is the function that we're going to be trying to implement? So I had done little kind of hardware computer consoles before, so this is kind of what I wanted to do again, like maybe a mouse and a keyboard and a screen. I decided the keyboard was too much work, and I feel like if you can choose between a mouse and a keyboard, the mouse is more interesting than the keyboard. There's kind of a subversive energy to that. because the mouse is like what you use to directly manipulate things. So the system diagram is kind of going to be like Omar's chip, and then like PS2 mouse and VGA screen. And that's what we've got. And you can see, here's where my chip would be, here's the mouse, and here's the screen. So the chip is generating, the white pixels and then the blue pixel. It's storing where the mouse is, and it's generating blue pixels for that, 24 times a second or whatever. How do I design the chip? Do I draw on pen and paper? Do I type it out in Microsoft Word? Do I make a spreadsheet? It turns out that it's surprisingly, at least for a digital design, which is like a CPU or GPU or something, it's surprisingly like programming. You write a bunch of code. This is the GitHub repository. It's actually public. You can go look it up. And you write in a hardware description language. So the ones you might have heard of are Verilog, VHDL. There's a bunch of more exotic ones that are probably better, but not used by anyone. And the one I use is called System Verilog. So this is some System Verilog code. It's like kind of a whole new way of thinking. You have to think in terms of like state machines, and it's kind of like functional programming. You draw all these diagrams of state machines and like ring buffers between the different parts of your chip, but I don't have time to talk about that. And now that I have the code for my chip, I need to convert this code description, which is just text, into a CAD file to send to the fab so that they can actually manufacture it, like cut it into the silicon. So there's this command, make harden, that I'm gonna run. And this is sped up a lot. This took 5 minutes in real life, which is still pretty fast for a chip layout. It has to do a bunch of stuff. It has to do synthesis, where it turns my code into a graph of like logic gates and like what logic gates should connect to what other logic gates. And then it has to do placing and routing, where it actually makes the concrete diagram of like, oh, what stuff has to be drawn where, how is it connected? And that's an NP-hard problem, so it's like an optimization problem. You get different results. It can take anywhere between 5 minutes and like 30 hours. If you talk to people in industry, it takes days to just get the layout, let alone to know how it works. Okay, we're done. This is the layout that I got out of hardening my chip design. So one fact that I think is really cool that I didn't realize and really important to emphasize, this is a view from the top. So this is like me looking down on the chip. If you've seen like decap chips or chip diagrams in passing, they usually look kind of like this. But this is not really how the chip actually looks. This is just like looking down. It's just like a planar view. If you look from the side, you realize that microchips actually have layers. And at the bottom layer is where all the logic is, like down at the bottom. And then the upper layers are all like interconnects, so like wires, kind of like on a PCB, like Liz was saying in the previous talk, are wires like connecting different parts of the chip. So when we look at this, we can actually, we can actually take this view and we can zoom in and we can rotate and kind of view it from the side. And you realize that this is actually kind of this whole 3D structure, where at the top you have these blue layers that are like the highways, and then as you go further down, you see that there are layers and layers of like at the bottom you have like local road. Well, at the very bottom you have logic, and then you have kind of local roads, and then and then streets, and then avenues, and then highways at the top. So when you're making a microchip, like all the chips in your computer are really these like 3D city-like structures, which is something I thought was really cool and not what I thought of when I first started this process. Okay. Yeah, so we have our code. So we had our Verilog code. We converted it to a CAD file with this whole 3D structure in it. And then we convert that into a chip. Or we send that to the fab in Minnesota. That's the fab. And then a few months or years later, this guy. Fun fact, I was told that less than 1/3 of what they call a chip tape out, where you send this to the fab, end up working. I have a friend who works for a friend from college who works for a major GPU company who would say that, yeah, you send it in, you get it back, it doesn't work. That's kind of like tens of millions of dollars down the drain. And in practice, I haven't talked about this at all, but you actually spend like half your time testing, or more. Even for this, I spend half my time testing. Probably in practice, in industry, you spend 80% of your time testing. But yeah, thank you all very much.